We're going to finish up on chapter 10 today and move on to oxidation reduction stuff. If you don't already feel like you're trying to drink from a fire hose, you will, because there's a lot of new reactions that we're going to be talking about, and your focus is going to need to be on the principles, the mechanism. You're going to have to memorize some things, but I don't recommend that you memorize it all. For example, if you know for alkene halogenation that there is no carbocationic intermediate, then you shouldn't need to memorize that you don't get any syn addition products from halogenation because there's no carbocationic intermediate that can be attacked from either side. You may have to memorize that there is a bromonium ion intermediate because that's something that's new that you haven't necessarily seen before. But once you see it, you shouldn't need to memorize that halogenation leads to exclusively anti-addition products because if you've learned to recognize a bromonium ion as basically being like a protonated epoxide, then the idea that it opens up via backside attack in an SN2 reaction should be clear to you. So you want to make the distinction between things you need to memorize and remember and things you can figure out based on what you know from basically first principles. All right, so we have talked about how if you want a 1,2 or vicinal dibromide, this is a structural pattern that you probably want to be able to recognize. If you see a 1,2 dibromide, you could have gotten that via the halogenation reaction. And the mechanism we discussed last time, it's a concerted mechanism where the pi bond attacks the bromine sigma star. At the same time, lone pairs on the bromine that gets attacked attached to the other carbon. So we never see a carbocationic intermediate, just a 3-membered ring bromonium ion, which opens up from the backside. I'll show you evidence in a little bit that it's probably the more substituted carbon that gets attacked. You can't tell though because either one gets a bromine. All right, anything you want to ask about that? Okay, so we're going to circle back, as I said, to something that we missed in the stuff about E2, and that is what can you do with a vicinal dibromide in any way. So some of you saw this on the study guide for chapter 7 and 8 and kind of wondered what was going on. So let's just say you take an alkene, you do alkene bromination, that gets you a bromine on carbon 1 and another bromine on carbon 2. And we might want to redraw this just to get it in the right sort of shape and orientation for an E2 type reaction. But basically notice that on carbon 1 you have a leaving group and there's a beta proton on carbon 2, a proton that can be anti to the leaving group, and so you should recognize that as a situation where an E2 reaction can occur. And then also you have a bromine leaving group on carbon 2 with a beta proton on carbon 1 that can be anti to the leaving group. So it shouldn't be too much of a stretch to see this as a molecule that can undergo 2 tandem E2 reactions. All right. The choice of base that's used in your text, you could use tert butoxide if you wanted to. The choice of base that's used in your text is NaNH2 or sodium amide. This is a base it's an inorganic molecule, it's a salt, and so it's not very soluble in organic solvent. Because it's not very soluble, it's not a good nucleophile, it's just really a good base. And it's a strong enough base to do the 2 E2 reactions. So remove the beta proton, make a pi bond. Does it matter, or do you know which beta proton gets removed first? What do you think? You can't tell. And it doesn't matter because they're both going to be gone anyway. So, oops, making stuff up at this point. Let's see. There we go. So we've made the first of our pi bonds. We removed a proton. Here's the conjugate acid of that base that we used, and then Br minus is our leaving group. But we're poised again for a second equivalent of NH2 minus to remove this proton, kicking off the leaving group and giving you your alkyne product. Okay? So this is one way we can make alkynes. And in fact, I think we haven't ever made an alkyne before, so there you go. Guess what? Here on out, if you need to use an alkyne as a reagent in a synthesis, chances are I'm not going to let you start here. I'm going to make you do this. Dang it, right? Why would we want to make an alkyne in the first place? Well, if you add a third equivalent of sodium amide, again, a really strong base, the pKa of the proton on the alkyne is 25, whereas the pKa of the conjugate acid of the amide anion is 38. So it's fast and easy to remove that proton. Once you've done that, you can do a bunch of SN2 type reactions using this as a nucleophile and generally using some kind of primary alkyl halide. We'll just use an ethyl halide as an example. I'm getting tired of writing Br, so we'll just use Cl maybe. And you can make a new carbon-carbon bond. And you saw this reaction in chapters 7 and 8, but you may not have appreciated it. This is one of our first carbon-carbon bond forming reactions. I think the only other one besides this that you saw is if we use Cn minus as a nucleophile. Carbon-carbon bond forming reactions are near and dear to the hearts of synthetic organic chemists because this is how you build up complexity in molecules. This is how you take smaller subunits and link them together to make larger and more interesting organic molecules. And this is a bond between an sp hybridized carbon and an sp3 hybridized carbon. So if you see a product that has an sp3 sigma bond, you need to be thinking, I could have made that via an SN2 reaction with an alkyne, which I could have made from an olefin via this series of bromination followed by double or tandem elimination. All right, so making an alkyne, then using it as a nucleophile. The alkyne nucleophile here, the deprotonated alkyne, you're going to hear me talk about it as an acetylide anion. You don't need to memorize that, but you should be able to not be confused when I say it. Okay? All right, let's talk about synthesis. I'm going to do some synthesis in the forward direction using this approach. And then we're going to plan some syntheses starting at the end and thinking about how we could have made the product that is indicated. All right, so suppose I want to make something bigger. I can now, because the alkyne product that I've made in this step has another acidic proton, here, right? Well, acidic is relative, but the pKa of that proton is 25. It would be totally fine for me to introduce yet another equivalent of my really strong base that can remove the proton on the alkyne. That gives me this more complicated acetylide anion. Acetylide we're using as a term for a class of molecules that have a negative charge on an sp hybridized carbon that's involved in a triple bond. So we would say this is an example of an acetylide anion. You can now do another SN2 reaction using another primary alkyl halide. In general, we want to avoid secondary alkyl halides because of the potential for competing elimination reactions when you're using a nucleophile that's also a strong base. And certainly this would qualify based on the pKa criteria that we talked about. So because I know rings of all kinds strike terror into your hearts, we will use that as our alkyl halide, and you can do an SN2 reaction. No, that other arrow was fine. Attack the sigma star from the backside, leaving group leaves, and now I've made a new carbon-carbon bond. Okay? Common mistakes people make with alkynes is forgetting where the alkyne carbons are. For example, it's totally fine for me to draw this molecule like, oh, haha, that's funny, triple, yeah. It's totally fine for me to draw this molecule like this. That's the triple bond. That's the bond between sp hybridized carbon and sp3 hybridized carbon on the right-hand side. Okay, sometimes people will do this and they will forget that this place at the end of either end of the triple bond is actually a carbon. These two are totally the same thing and you can draw them this way. In my experience, students in 351 sometimes struggle with this, so just go ahead and draw the carbons in the alkyne. Save yourself some heartache. Another mistake people make with alkynes is they think, oh, well, this is the, up here we've got the cis isomer. I'm putting that in quotation marks because that's wrong. And then they will draw the same molecule like this and say, oh, that's the trans isomer. What's wrong with that? There's no cis and trans around triple bonds. You're talking about the difference between these two shapes is an issue of rotation around carbon-carbon single bonds. So yeah, you can draw it any way you want. Those things are propelling around. Those R groups on the end of the alkyne are propelling around constantly anyway. Those are not stereoisomers. So a common mistake, not necessarily a hugely consequential one, but one that I've seen students make. The biggest one is forgetting that there are carbons at either end of the triple bond. Okay? What do you think about this? Feeling okay about that reaction series? Make an alkyne, deprotonate the alkyne, SN2 to install one R group on the right side or the left side, whichever hand you're looking at, and then another deprotonate the alkyne and then install an R group via an SN2 reaction. Okay. Yeah?
What is this called? Is this still part of halogenation?
What is this called? I don't know. Like halogenation is the reaction where you make the 1,2 dibromide. You're halogenating the double bond or the pi bond of the alkene. This reaction series, the first step is halogenation. The second step is acid-base. The third step is SN2. The fourth step is acid-base. The second, or the step after that, fourth one. Sorry, fifth. That's the one that comes after fourth. Is SN2. Yeah. So, but this synthetic series, make an alkyne and make sp hybridized carbon-carbon bonds, is one you ought to get used to. It's a way to introduce the concept of synthesis, and it will get worse in 352, but the strategies you use to think about how do I make this molecule will continue to be useful. Okay, what else? Yeah?
Can you do the alkene halogenation with chlorine or iodine or
Can you do alkene halogenation? Works good with Cl2. Your text actually doesn't talk about I2. I think that's probably possible, but probably not necessary. And then F2, I haven't seen either. Fluorine gas, I think, is highly reactive and poisonous, so it's generally a bad idea to use that, unless you're in an industrial setting with a pressurized reaction vessel. I2 is actually a solid, Cl2 is a gas, Br2 is a liquid. Working with any of these is kind of difficult. I2 is maybe a little bit easier because it's a solid. I don't know. Somebody knows, I just don't. But you can use Cl2 and Br2 interchangeably here. Okay, what else? Ooh, let me make it worse. Thank you. Yes, you're welcome. Because you now, because of the elimination chapter, know how to make olefins too, or alkenes as well. So I could have you start with an alcohol, and then you might use, for example, POCl3 and pyridine, or you might use PBr3 to generate the alkyl bromide and then do an elimination reaction to get the alkene. At this stage, there might be reasons why you would do one versus the other, but as long as the chemistry works based on reactions that you know, the synthetic pathway should be fine. In general, in synthesis, one mistake people make is inventing reactions. Like, inventing reactions is cool. They do that in Professor Michaelis's lab and in Professor S's lab. But generally, if it's you on a test, inventing reactions is a bad idea. However, I always open it up to you. If you can find an example in the literature where your made-up reaction actually works, then I can give you points for it. That would be on a free response exam. It's pretty hard to make up reactions when I constrain your options, I guess. But okay, let's think about synthesis in the reverse direction. I'm going to show you, again, we're building up your tolerance to horrible ring-like structures. Let's see. We won't worry about stereochemistry. Yeah, that's fine. Let's just make it not a stereocenter. Okay. So I want you to make this from allowed starting materials include, well, actually, no, I'm not going to do that. I'm not going to even tell you what starting materials you can use. You can propose stuff and I'll say, no, actually, you can't do that. All right, make this product, and you have to do it from, you have to use at least the following starting material. Other than that, you can use any reagents that you want, but you have to use this one. That's fun. So what we're going to do now is something that's called retrosynthesis, where you try to develop a plan going backwards for how you're going to do a reaction. This is kind of a hard concept to introduce or work on because at first you're going to feel like it doesn't make the situation any better, but our goal is to gradually step backwards through the synthesis to get to ever simpler starting materials, and that will develop a plan. So where I like to begin is I look at the product and I try to identify bonds in the product that I know how to make. Okay, well, what bonds do I know how to make here? Any ideas? I told you you want to look for that pattern. This is why, right? Do you see any sp3 sigma bonds? Yes, right, that's a good primary question. Actually, when I ask obvious questions in primary, everybody tries to be a comedian and give me exactly the wrong answer. Should we sing whatever song? No. And whenever somebody gets mentioned that they have a birthday, everybody else needs to chime in that they too have a birthday. How many people have birthdays, right? Yeah. Okay, so sp to sp3 carbon bonds. You got one here. I'm going to use a red squiggly line to indicate I could have made that bond. And though this isn't necessarily part of retrosynthesis, I'm going to write here what reaction I could have used to make this bond. What do you think? What is the reaction I used to make an sp to sp3 carbon-carbon bond? Okay, it's that leaving group and alkyne reaction, right? Sort of that SN2 reaction. Okay. What other bonds do I know how to make here? I could make the one on the other side. All right. Yeah, let's talk about that. What do you think the starting materials would have been for making that bond? Another alkyne, right? And again, this is an sp to sp3 carbon-carbon sigma bond. Okay, if you want to do an SN2 reaction, this was your nucleophile. What do you think your electrophile would have been? Go ahead, somebody take a risk. You want an alkyl halide here, okay? Okay, that's a reasonable strategy. There's an issue with it that I want to help you see. What do you know about this acetylide anion in terms of its characteristics as a nucleophile and a base? It's both, right? It's a strong base and a strong nucleophile. The conjugate acid of that base has a pKa of 25. Now, look at this. Do you see any protons whose pKa's are less than 25? Yep. Right air, as my nephew says. 16. So probably you're going to be worried about the potential for quenching your nucleophile simply by removing the proton on that alcohol. And so there's a better way. This isn't a bad one, and I've given on free response exams way back in my previous history, I would give some credit, a lot of credit, maybe full credit for that answer, but there's a better way. Using an electrophile that does not have an acidic proton, okay? I'm just trying not to reveal it to you because I want you to try to come to the conclusion yourself. There's a recent molecule that we used where I told you that a reaction with that molecule leads to an important structural pattern where you got an OH on one carbon and what used to be a nucleophile on the adjacent carbon. Sort of a 1-2 substitution pattern. What? What was that word? Epoxide. Okay, we talked about an epoxide where if a nucleophile opens it up in your product, you end up with 1-2 relationship between nucleophile and OH group. So, if my nucleophile was this acetylide ion, what would the epoxide have been? Okay, well, triangle, sure. 2 methyls. Okay, good. And 2 protons. Let's check and see whether that works in terms of regioselectivity. Strong nucleophile, strong base should open up an epoxide at which carbon? Less substituted one because SN2 and sterics, right? Okay, so yes, that works. I think there are problems like this on the practice exam or in the text. Once you've seen it, it's kind of hard to unsee, and you can use it as a strategy. But you want to practice this kind of thing until you're able to do it when I'm not sort of hovering over your shoulder whispering answers, right? Like that. That sounds kind of scary, actually, kind of creepy. Okay, so now we've got sort of a plan. We're going to use a retrosynthetic arrow. That's this weird double arrow, and and it actually doesn't matter. We could decide to make this bond first or maybe this one. I'm going to have us, I'm going to want the last step to be this carbon-carbon bond formation because I don't want that OH group hanging around while I try to do chemistry on this side, because I'm going to have the same problem with removing a proton on an OH group. So let's have this bond formation be our last step. So the starting material for that would have been this alkyne, which we would deprotonate to make a nucleophile, and then this epoxide. Okay? And I told you that any and all reagents were fine. You just have to have this be one of your starting materials. So that's an allowed starting material. We are done with this part of the molecule. All right, now let's step backwards and make this bond. The starting material for that would have been this alkyl halide, whatever we want it to be, and this alkyne. This is an allowed starting material, but we haven't yet used this one. So now we need to think, how do I get from an allowed starting material to this alkyne that I need? Go ahead.
Does using the epoxide give us wrong stereochemical configuration? Because isn't it supposed to be the S configuration instead of the Z configuration?
SZ. Configuration where? Sorry.
I mean, the
E and Z about where?
about the triple bond goes in, and then on the same side, the OH comes out. Should it be?
Yes. So you're noting that I showed it looks like the OH and the alkyne are syn to each other. They would be anti. That's absolutely true, but the carbon you make is not a stereocenter, neither is that one, so I've just rotated around a carbon-carbon bond. Yeah. Okay, what else? Okay, how do I make an alkyne from this starting material? Scroll up, go ahead.
You first do the reaction, make it the alkene,
Okay.
and then you halogenate it with dibromide.
So you go from the vicinal 1,2 dibromide to the alkene via this sort of tandem E2 reaction approach. We can get that dibromide from this alkene, and then do you know of reactions that convert this starting material to this alkene? You better. it's a classic sort of E2 elimination reaction. And now we are here at an allowed starting material. Okay, that's the process. Breaking it down into ever simpler subunits. Okay, so now the burning question is this going to be on the test? Or is this important? Or do we need to know this? And the answer to all of those questions is yes. Everything I say is important. You don't find that funny, I do. It's true that not everything I say is important. But in any case, this stuff is important. Now, how might you see it on a test? Well, likely on an exam, it's difficult in a multiple choice exam to sort of give you this product and say make it and then just grade your synthesis whatever it is. I have to give you some options. So the way this would have appeared on an exam is there would have been a big question mark here. We would have had this be the starting material. We would have had this be the product. And then there would have been options A through triple Z. Actually, the testing center doesn't let me do that. So A through whatever. And there would be a list of reactions that you could do on this starting material that would end up with this product. And there would be lots of options, and only one of the options would work. Dot, dot, dot means more than that. And for example, the way I would have written this synthesis, the correct synthesis of this molecule as one of the answers, do we have enough space if we zoom in? Sure. We would have used tert butoxide first to make the alkene. Then we would have done halogenation to give you the vicinal dibromide. Then I would have used the base NaNH2, and I would have used 3 equivalents of that to make the alkyne and deprotonate it. Then step 4, I would have done the SN2 reaction. I would have needed another equivalent of base to deprotonate the resulting alkyne. Then we would have brought in the epoxide, and we're done. Okay? So that would have been one of the options, and then there would have been other choices here. And some of these options that are distractors, that are not correct, will have plausible but incorrect reactions afterwards. Yeah?
What's the likelihood that she'll give us the same molecules, but in like the wrong order?
Does order matter? Yes. Could I give you the same list, but the order could be wrong? Yeah, though, let's see. How would that even make sense?
Based on what you said earlier, if you gave us the epoxide earlier, we would have had issues with the OH.
Yeah, if you had tried to do the epoxide earlier, you would have then been trying to make this carbon-carbon bond in the presence, with a strong base, in the presence of an OH group, which could have been problematic. That wouldn't have been totally incorrect. That would have been partial credit. Likely what would have happened is I would have given 0 credit, and then some of you would have come to talk to me and sort of talked me down from being a jerk, and I would have given everybody partial credit. Right. So at this stage, the synthesis is pretty straightforward in the sense that I'm having a hard time thinking of bad options. Let's see if we can come up with a bad option. Sure, okay, here's a bad option. Let's use as a base sodium methoxide, and then we'll keep everything else the same. What's my problem there? Okay, so here's the robot waving hands and saying, warning, 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 don't do that. The problem is, as you've noted, this is both a good nucleophile and a good base and your starting material is a primary alkyl halide. So what you're going to get from here is just an ether, and then you're done. Dun, dun, dun. Yeah.
So in your step 5, the second step with sodium amide, which
Yeah.
step does that correspond to?
That corresponds to here, where we first need to remove this proton and then have it act as a nucleophile on the epoxide.
Okay, so that one's to remove. Okay.
Yep. Others? Yes?
So what would happen if, just for the sake of this, if you added 4 equivalents of NaNH2 in step 3?
Oh, step 3, sorry. Big sigh. Actually, so what you're saying is 3 equivalents gets you here. Does the 4th equivalent remove that proton? Once the molecule's already negatively charged, the pKa of that second proton goes up dramatically. So no, basically wouldn't do anything. Yeah.
I thought that the epoxide, you would use the H that was already in the C, like the triple bond of the H, to just dump onto the top of, like the H would go onto the O and then it would kind of break. Or do we need to break, or do we need to get rid of the H with the NH2?
So before, I mean, really for this SN2 reaction to work, to open the epoxide, you need to have the negatively charged acetylide. This is not a strong enough acid to protonate the epoxide. Remember, a protonated epoxide should have a pKa similar to a protonated alcohol, about -2. So no way are you going to take a molecule that has a pKa of 25 and protonate the epoxide with that. So no, you have to have the base to remove the proton first, and then you introduce the epoxide. Yep. Let me see other ways to screw this up. I don't know. Can't think of any. Maybe, what about some pointless roundaboutness? Pointless roundaboutness. Let's see. Oh, sure. Sure, we'll pull out all the fun ones. And then suppose from that point on it was the same. Yikes. So the problem with this one is, well, actually, I meant it should have started with there. Problem with this one, okay, you make the double bond, then you do hydroboration oxidation to put an OH group back on there for whatever painful and dumb reason. Then you say, okay, let's get the double bond back with POCl3 and pyridine. And at this point, I'm hopefully, or rather for my distracting incorrect answer, I'm just throwing spaghetti at you to see if I can confuse you. Some of you are going to say, I vaguely remember studying TSCl and pyridine, and it did something, so this must be the right answer. Bad strategy. Okay? So what I will recommend on synthesis problems on the exam is that you actually try to start the problem this way. Think backwards, do it on scratch paper. You're always welcome to staple your scratch paper to the exam. If the testing center gives you a bad time about that, tell them that I said you could. I don't know if I have any clout over there, but it'll at least give you something to say. And if you want me to look at your synthesis plan after the fact, I totally can. But once you've planned something out and you think it's reasonable, then go to the answers and see if you can find your answer there. It may take you too much time and be too confusing to try to go through all of the answers step by step and see what they do. If you're gonna do that, do it systematically on paper and not in your head. Treat each of these as like a predict products question, and you'll fairly easily find the missing weird steps. For example, we talked about that issue here. If you'd said, okay, well, let's just try this one out. We start with the alkyl halide. You use sodium methoxide as a base / nucleophile. Oh, okay, well, SN2 reaction, we're done. That can't be it. Similarly, if you had followed this down and through the bewildering mess of unnecessary reactions, what the heck do you do with tosyl chloride and a alkene? We used to react tosyl chloride with alcohols, which that isn't one, so that doesn't make sense, and I could rule that one out. Okay. Anyway, don't want to beat that one to death, but it's worth some practice, because I can guarantee you will find some problems on the exam that will be this way. So you have been warned. Okay, yes?
You don't need to show the step of protonating the epoxide after.
Do you need to show the step of protonating the epoxide? It certainly would not be incorrect if you did. For any of these steps in a synthesis, you can assume an aqueous workup after the fact to protonate whatever needs protonating. I'm always unsure of what to do, because if I do this, some people are going to say, well, okay, you protonated the epoxide, but didn't you say that actually acid and alcohols is dehydration conditions, and couldn't you get a double bond there? And that's why I didn't choose that answer. So to avoid that conversation, we'll just say that mild aqueous workup puts protons back on.
So whenever something needs a hydrogen produce, assume
That is a very broad blanket statement. Whenever something needs a hydrogen, we can assume that it will be there. No. Whenever you have a product like the product this one would have been in a synthesis, let's see, this would have been the immediate product, negatively charged oxygen. Yes, you can assume after that there's going to be aqueous workup that puts a proton back on. That's, yeah. Okay. So that's chapter 10. There's a bunch of stuff in chapter 10 about using alkynes in addition reactions. There's not a lot of new concepts there. It's just more application of stuff that you've already learned from, like halogenation and hydroboration, oxidation, and so on. So we're not going to do that. I do need to, before we move on, point out one. I promised you some evidence for the fact that it seems like the Br- attacks the more substituted carbon in the second step of halogenation. Enter reaction 5 for the chapter, which I don't even think is a separate reaction. Your book calls it halohydrin formation. And at this stage, you get the sense that the text just likes words that end in ation. And if that helps you, that's great. You can take the same starting material, and you're going to use either Br2 or Cl2, but this time you're going to use water, or it could have been an alcohol as a solvent. And the idea here is that when you're using water or an alcohol as a solvent, it can outcompete Br- in the second step to open up the bromonium ion. So I'm going to draw one of the two bromonium ions. I'm going to put a plus- here to indicate that we get the other enantiomer. Now, previously for halogenation, we had Br- act as the nucleophile in the second step to open up the bromide. But when you're using water or an alcohol as solvent, bromide sort of floats away, and is replaced by tons of water molecules. And now, because I told you to think of the bromonium ion as a protonated epoxide, we're going to open it up with water in the same way we would have opened up a protonated epoxide, and we're going to do so at the more substituted carbon as we did for protonated epoxide, because that's where the buildup of partial positive charge is best tolerated in the transition state. And so then your product involves inversion at carbon A. The water that came in should be here and down. The methyl group is inverted up. Br here is up, deuterium is down. And then aqueous workup will neutralize this protonated alcohol to just give you this alcohol product. This is supposedly called a halohydrin. You got an OH and Br on separate carbons. Notice the stereo and regiochemical issues. We get anti-addition because we have no carbocationic intermediate. And regioselectivity, the OH ends up on the more substituted carbon. And of course we get the other enantiomer. Now, had I used methanol as the solvent, then instead of an OH group on that more substituted carbon, I'm going to have an ether. So that product would be this one. With its enantiomer. So you can see why hopefully I don't even think of that as its separate reaction. It's exactly the same, just one more detail that creates a slightly different outcome. All right, I meant to move on to chapter 11, which is oxidation and reduction. We didn't quite get there. We are moving on to that next time. By the way, Friday is spring day, so enjoy your one day off, and I'll see you on Monday.